about significant figures, and then we are also doing exponents. So remember, if your number is less than 1, if I give you like the whole number, it's less than 1, and you have to change it to scientific notation, you're always going to make your number between what? 1 and 9. Okay, so that just means you find the decimal place. Doesn't matter if it's at the very beginning or at the very end. Wherever your decimal place, you're going to move the decimal place to make your number between 1 and 9. So for this one, I'm going to go, maybe, I'm going to go 1, 2, 3, 4, 5, 6. So since my number is less than 1, this is going to be times 10 to the 6. Negative 6, right? So remember, if your number is less than 1, the exponent will always end up being a negative number. If it's greater than 1, it's always positive. Now, the only thing that I can leave out front is I need to have only significant figures in the number out front. So what happens to those zeros out front? They disappear, right? Remember, zeros out front are never significant. What about the ones at the end? I need to keep those because remember, they're after the decimal place. So all of these are considered significant figures. So I would have 4.5100. And this is my crazy pen. I have a pen that's way too sensitive. 4.5100. It makes spider web marks all over everything. Okay. Now what about this one? Where's the decimal place if you don't see it? At the very end, okay? And so I'm going to just move that decimal place until I make my number between 1 and 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that means this is times 10 to the positive 14th because it's bigger than 1. Now, significant figures. In that number, how many significant figures are there? Just one. Just the one out front. So that means I just have a 1. So the number that goes out front is only significant figures. What about this last one? If I had to go to the normal form, which way is that decimal place going to go? To the right. How many places? So how many zeros at the end? 2. So it would go 1, 2, 3, 4. So I'd have to add 2 zeros to make 5, 6. So 9, 5, 1, 2, 3, 0, 0. So notice that number in scientific notation and that number written out, they both have 5 significant figures. Those zeros at the end show me how big the number is, but it doesn't include those significant figures. Okay, so over the weekend you did the unit conversions, you did the scientific notations and such. So there's really just a couple of things left in chapter 1. One is percent. So percent is a math calculation that's covered in chapter 1 because we actually end up using it quite a bit. And people are most comfortable with percent when thinking about how much it is out of 100, right? So if you get an 80% on an exam, then that means that you got 80 points out of 100 possible. So the part is what you got, an 80, divided by the total possible points, which would be 100. Now, if I divide that, 80 divided by 100 would be 0.8. So thinking about things in terms of a decimal or a fraction is not as comfortable for people. So that is why you take that and multiply this answer times 100. And that's actually how you get that 80%. So it would be your score divided by the total possible score times 100, puts it everything on a scale of 0 to 100. So instead of saying, oh, well, I got 6 out of 7 right, or I got 9 out of 25 right, you have it on a scale of 0 to 100. So that's how you do in percent. The calculation for percent is always what part out of the whole times 100. So however much you got divided by the maximum you could possibly get times 100, and you would still make sure that you apply significant figures in your answer. Okay, so the measured number is typically the part, so you would always add those significant figures. So here's one that's pretty simple. So you have 48 coins. Okay, so 48 coins, 12 are quarters, 20 are nickels, 10 are dimes, the rest are pennies. And so the question is what is the percent of each? So what is the percent quarters? How do I figure that out? 12 divided by Nope. What is the total? 48. So it's the number that are the parts, so that is the part that are quarters, divided by the total number of coins, because they don't necessarily have to be 100. So 12 out of 48 are quarters. Multiply that answer times 100. And if you need a calculator, calculators are up here. So 12 divided by 48 ends up being like 0.25. And then multiply it times 100 gives you 25%. Okay, so how are you going to figure out how many are nickels? So 20 divided by 48. Multiply that answer times 100, and what do you get? 31.666667%. Sorry, I don't have my calculator. I was just listening to you. I thought I heard 41, but maybe. Okay. So now with this, looking at my numbers, so these are like exact numbers, 48 coins, 12 are quarters, 20 are nickels. So in this one, how many significant figures in 20? There's actually only one, right? Because 20, the 0, if I don't have a decimal place, there's actually only one significant figure, two significant figure. So what would I have to round my answer to? One significant figure. What would I have? So the first significant figure would be the 4. So what would my answer round to? The next is a 1, so it would be 40. Right? So I'd round, the 4 is the one that I would keep. It's one significant figure. The next number is a 1, so it would round down to a 0. I need to have 40, not 4%, because it's showing the size of the number. So that 0 at the end of 40, it's not significant, but it shows you how big the number is. So now what about this one? So 10 are dimes. So that's 10 out of whatever answer you come up with, multiply it times 100. So what about this one? How many significant figures in 10? 1. How many significant figures in 48? So my answer has to have just 1. So 20.83333 rounds to just 20. And then it says rest are pennies. So how do I figure out how many are pennies? Okay, quarters and nickels and dimes, and then subtract that from 48, the total, right? So this is my total number. So if I took 48 and I subtract 12 and I subtract 20 and I subtract 10, how many are pennies? 6. So 6 out of 48 are pennies. Six divided by 48 times 100. Always times it by 100, because that's going to put it on your scale of 0 to 100. And that ends up being 12.5%. Now in this one, what would I have to round that to? Just to 10, right? Because 6 is one significant figure, 48 is 2. So I know I got to round my answer to one significant figure. So 12.5, the 1 in 12.5 is my significant figure that I'm going to keep. That means the 2 gets rounded down. So this ends up being 10%. Okay, but now if I add all those up, 25 plus 40 is 65. Plus 20 is 85, plus 10 is 95. Do you notice that they're not 100? And that all comes into play because of rounding. Because if you round numbers, then you may increase or decrease that number. So you may not end up coming up with like the total, equaling it back because of that rounding. So just know that you don't want to round until you get to the end. And since my question, the end of each of my questions, I just wanted to know the percent of each coin. So I would have to round those. But if I wanted to know like the relative percent, then I would have to keep those numbers. So here's one more to try out for percent. So this one says 2 infants are in PICU. So it's the perinatal ICU. So it's babies that have been born. One infant's weight increases from 126 ounces to 147. The other infant's weight increases from 86 to 103. Which infant had the greatest percent weight increase? So if you just look at them, which one do you think gained more weight by percent? Okay, so you think infant 1. Okay, because it looks like it started off, it's a bigger baby at the end. So let's do the calculation. So to figure out percent weight increase, how do I do that for infant 1? So 126 is their initial weight, 147 is their final weight. So I want to know what is their percent weight increase. So what do I have to do? What's the increase? You have to subtract them, right? Because the percent weight increase is how much of a change did their weight have. So I've got to take 147 and subtract 126, and that is 21. So baby number 1 gained 21 ounces. Now I have to divide. Do I divide by what they started at or at their final? So if their final is not really comparing what their change was from the beginning. So if you're looking at like, you know, when you think about weight loss, it's from where you started at, right? So same thing, it's their weight gain. You start from where they started at. So you would divide it by 126. So I had a change of 21 ounces from the initial of 126. Multiply that answer times 100 because that's going to give me a percentage. And I got 16.6666667%. Significant figures, what would I call that? 21 and 126. So I'd want 2 significant figures in my answer, right? Because there's 2 significant figures in 21, 3 significant figures in 126. So I'm going to keep the 1 and the 6. Next is a 6. So what does that do? Round up or down? It's going to round up to 17, so 17%. Okay, so that's infant number 1. Let's do infant number 2. So infant number 2 went from what? To 103. So the difference?
You said 2 significant, so you went around the third 6, so it's the second 6?
So the 2 significant figures, the 1 and the first 6 is significant. The next number is a 6, and that tells me to round my 6 to a 7. So infant 2, I took 103 and subtract 86, so that is 17. And then divide by. So you're not going to divide by their final weight. You want to divide by what they started at. So it'd be divided by 86. And then that answer times 100. Because 100 is going to put it in percent. So 17 divided by 86 times 100 is going to be 19.76744419%. Now, if I want to round this one.
Do you consider that as 2 significance?
Because the 17. So see in this, so now when I go back to figure out significant figures, 17 has 2 significant figures. 86 has 2 significant figures. The first 2 digits from the left is the 1 and the 9. The next number is a 7. So what's that going to do? It's going to round it up. So instead of 19, it'll be 20. How do I show 2 significant figures with 20? Add a decimal. Right? So if I add a decimal, zeros at the end are now significant. So that shows 2 significant figures in my answer. And so baby number 2 actually had the greatest weight increase. So sometimes when you look at numbers, if you look at like a change, where if you're doing a comparison and you have different numbers of the total, you really putting it into percent can allow you to really compare them, because putting things in percent puts it on a scale of 0 to 100. Instead of like looking at 86 ounces versus 126 ounces. So being able to put it on that percentage can help. So things that you're going to see in medications is you will oftentimes have dosages. So this is looking at a dosage, and you look at it and you're like, oh no, it's a word problem. All you want to do is you want to pull out, what do I know and what am I trying to find? So the first thing is it says a patient receives an IV with nitroglycerin infusing at 8 milliliters per hour. Okay, so that means that I'm giving this patient 8 milliliters of that medicine per hour. Okay, that's being evenly distributed over that course of time. It says the concentration of the solution to be added to the IV is 50 decimal place milligrams of medicine, nitroglycerin, per 250 milliliters of D5W. And so D5W is just, that stands for dextrose. That's the D, 5% in water. So all it is sugar water, but it's sterile sugar water, so it can be given as an IV. So this, kind of like we talked in another one, so this 50 milligrams of nitroglycerin per 250 mils of D5W, that's a solution. And remember, solutions are like a mixture. So I have 50.0 milligrams of this medication divided by 250 milliliters of a solution. So it's saying the same thing. Remember, if you see something and then that slash, that you can think of it as, it means that they can be this way, but I could also flip it. I can use this like a unit conversion when you have this ratio of material. So the question I want to know is, I want to know how many milligrams per hour. Well, I know milligrams in that number. The solution says there's 50 milligrams of medicine per 250 milliliters of solution. What's the rate that I'm giving this medicine? So I know that I am giving them 8.0 milliliters of the solution per 1 hour, because it's actually asking milligrams per hour. So if I set this up, what do I need to cancel?
The milliliter.
Get rid of milliliters, because of my answer I want is milligrams per hour. Right? So I want to get rid of milliliters. So how do I set it up so that milliliters and milliliters will cancel?
You write it on that side.
Okay,
Like
so
that.
50 milligrams per 250 milliliters times
8 milliliters.
Mhm.
In 1 hour.
Right? Yep. And what happens to milliliters? Milliliters and milliliters will cancel. Okay? So setting it up this way, milliliters and milliliters will cancel. And see, your units are in milligrams per hour. So now, what math do you do? What do you multiply? 50 times 8. 50 times 8.0 and divide it by 250. It ends up,
You gotta have a decimal behind 0.
oh, because it's exact. That's what I was trying to say. It's like an exact 50 rather than being a random like number. So I ended up with 1.6 milligrams per hour. So that's how much nitroglycerin you're giving that patient per hour. But setting it up and keeping track of your units this way can help you make sure that you do it so that you're multiplying when you should and not dividing, so that you set it up. Always track with those units, and you'll know that your answer you're coming out with has the right units and you're doing the math right. So just 50 times 8 divided by 250 ends up coming out as 1.6. Now, if I go back and I look at my numbers and I think about significant figures, do I need to change my answer? How many significant figures in 8.0? 2. How many significant figures in 50? Well, it's got a decimal place, so that makes, right? That's why I put that decimal place there. So that's 2. Okay, and then 250 mils of D5W. So it's just 2, right? Because the 0 at the end is not significant if there's no decimal. Remember, zeros at the end are not significant unless there's a decimal place. So they're all 2. So am I okay with this? Yes. 1.6, 2 significant figures. So I don't need to round that. I would keep it. So once you get an answer, go back and look at the measured numbers in your problem and compare that, because if I had ended up with like 1.56777893, then you're going to have to round that. And that's how you go based on. This one just happens to work out. I don't have to round it because there's 2 significant figures in this answer as well. So everything works. Okay? So the second kind of topic to finish up in this chapter is density. So we've talked about mass. So we said things that are in mass, they're measured in grams. We can have milligrams, we could have kilograms, we can have larger and smaller measurements, but mass is an indication of the amount of substance something has. And that common base unit is the gram. Really, when we talk about mass, we think about weight. And so we talk about, weight is really mass relative to the gravitational pull of the Earth. So they're pretty equivalent, but it is a little bit different. You would have the same mass on the moon as you would on the Earth, but you wouldn't have the same weight. So that's a little bit of why the variation comes about. Volume is the other thing. And volume, remember, is all matter, has mass, and takes up space. So volume is the amount of space a substance takes up. Volume can be measured with the liter. So the base unit is the liter. We could measure in milliliters. We can measure in kiloliters. When we're talking about solids are commonly measured in what they call cubic centimeters. And they use cubic centimeters because solids have a height, a length, and a width. So when you multiply length times width times height, that will give you, like, measured in centimeters. Centimeters times centimeters times centimeters gives you centimeters cubed. So that's where cubic centimeters came about. So they'll have cm with a little 3. That's a cubic centimeter. Liquids, on the other hand, are typically measured in milliliters. So solids are usually cubic centimeters. Liquids are commonly milliliters. And one of the ways they came up with liters and milliliters is they determined that if you took 1 milliliter of water, if we could put it into a little cube, 1 milliliter of water would take up 1 centimeter by 1 centimeter by 1 centimeter. So if you put it in a container that was like a little block, it'd be 1 centimeter wide, 1 centimeter tall, 1 centimeter deep. So that is why 1 milliliter and 1 cubic centimeter are equal. So oftentimes in a syringe, it doesn't say milliliters, it'll say cc. Have you seen like a 3 cc syringe? That's a cubic centimeter. So milliliters and cubic centimeters, cc and ml, are equivalent and are commonly used in giving volumes of medication. So just know that. Don't let that throw you. When we talk about solids, we usually talk about cubic centimeters. When we talk about liquids, though, in chemistry, you usually talk about milliliters. If we're talking about gases don't fit into this. Gases are huge, right? Remember that they like to spread out. So gases are commonly referred to as being in liters, rather than being in tiny little milliliter volumes. When we talk about gases, we tend to talk about bigger volumes just because gases like to spread out so much. We can compress them, but if they're given their opportunity, they're going to spread out. But all those are volumes. So if you have a lump of aluminum, like a big pile of aluminum, or if you have just a little piece of aluminum, the mass is going to be different. The volume that it takes up is different. But because it's the same substance, if you take and compare its mass to volume ratio, that stays the same. And that's what density is. So density is a known value for any pure substance. So if I had any element on the periodic table, like aluminum, whether I had a big pile of aluminum or a little piece of aluminum, it would have the same density because the amount of its substance divided by the volume it takes up ends up being a constant number. So density is always going to be mass divided by volume. When coming up with density, they said, well, we like to have things like nice and common, like nice and uniform. So water was really the reference value for density. Water has a density where 1.00 grams of water will take up exactly 1 milliliter of volume. So that was sort of the starting point for determining density, and everything else is really in comparison to this. Which makes it nice because then that way you have something that's sort of a standard number, and everything was built sort of after this. You know, if something is less dense, it's going to float. If it's more dense, then it's going to sink. So if you have things that don't mix together. So their example, a piece of wood. So you know that wood is less dense than water because it floats on top of the water. If you drop a penny into water, it drops to the bottom. So I know that that metal is more dense than water. So you could do a comparison. If you had something you didn't know what it was and you knew that its density was greater than 1, that tells you some information about it. When you get a problem in density, you always know 2 of the 3 numbers. And here's the formula. It's always going to be density equals mass over volume. But now sometimes I might know density and volume and I have to find mass. I might know mass and volume and I have to find density. I might know density and mass and I have to find volume. You will always know 2 of the 3. So sometimes we'll have to rearrange this formula to figure out what we're trying to find. So you read the top one, you tell me which do I know? Do I know density, mass, or volume? So you know density, right? So things I know. Density is equal to 1.29, and this is grams per mil. Remember that means 1.29 grams over 1 mil. Right? So it's saying the exact same thing. It's just, I can write it like it's a unit conversion where I have a line and one above, one below, or I can put grams per mil just to sort of shorten it. But just know that's saying exactly the same thing. What else do I know? I know volume. I know that is 1.00 liters. So what do I want to know? Mass. Okay? So if I look at the formula, density equals mass divided by volume, D equals M over V. In order to find mass, I have to get the M all by itself. So now you got to think back to your algebra in the rearranging of formulas. What do I have to move to have mass all by itself? Volume, right? So volume's on the same side that mass is on. I've got to move volume. How do I move volume to the other side? I have to do what to both sides? Times both sides by times V. So if I say times V, you remember that? So if you have something in the denominator that you want to move to the other side, multiply both sides by that unit, because see what it does to the volumes. That will make volume and volume cancel. Now, volume times density is equal to mass. Now I have mass all by itself, and so I can just plug those numbers in. So I always list what I know and what I'm trying to find. Rearrange the formula. Whatever you don't know needs to be all by itself on one side of the formula. It doesn't matter if it's on the left or the right, but it needs to be all by itself. Now, before I just multiply volume times density, I have to double check units. So when I look at density, the units for density are grams per mil. The unit for volume is liters. So will my volumes cancel when I multiply these? If I have milliliters and liters, will they cancel? No. I'm going to have to change. So see in the units, I'm going to have to figure out how many milliliters my volume is. Then that'll put my milliliters and milliliters the same, and those units can cancel when I multiply. So if I have 1.00 liters and I want to know how many milliliters, this one's easy because it's only one step. Times in a line. What goes on the bottom? Whatever you start with always goes on the bottom. So what goes on the bottom? Liters goes on the bottom, right? And then your answer is milliliters. That goes on top. When you see milli, what do you put in front of it? 1,000. Milli gets 1,000. The base unit is the 1. Milli is 1,000 times smaller. It takes 1,000 millis to make a base unit. So now see how liters and liters will cancel. So 1 times 1,000 is 1,000. So instead of 1.00 liters, I'm going to use that 1,000 milliliters. So now I'm going to use this formula. So volume, 1,000 milliliters times density, which is 1.29 grams over 1 ml. So now see how ml and ml are on opposite sides, one above and one below. So those will cancel. So now when I do this math, 1,000 times 1.29 is 1290. In units, grams. Where's my decimal go? The decimal's at the end. So 1,000 times 1.29 is 1,290. Now I got to go back and double check my significant figures. How many significant figures here? 1.00. All the way at the top. That's my measured number, right?
3.
So it'd be 3. So how many significant figures in my answer? 3. So I'm all good. Now density.
But didn't you have a decimal?
Where?
Oh, I'm sorry.
The 1.29 had a decimal, but when I multiplied it times 1,000, the decimal moved over. Okay? Density, I didn't measure. Density is a known value. Kind of like, it's like what's on the periodic table is known. So I never would use this to round. So density is something that I didn't measure myself. Density is a known value. So I know the 1.00 liters is a measured value. So I would use that one for rounding. And this has 3 significant figures, the 1, the 2, the 9. 0 at the end, there's no decimal, so it's not significant. So I can just leave that one. Okay, so I want you to try this one. So 1, write down what you know. 2, figure out what your unknown is. 3, rearrange the formula. Because you know density equals mass over volume. Make sure you have the unknown all by itself. 4, check the units. Make sure the units that cancel are in the right value. Then 5, do the math. And apply significant figures. All right, so what do you know? I know mass. Okay, so mass is what? 678 milligrams. What else do I know? I know volume. So volume is 0.17 milliliters. And then what is my unknown? Density. So density. The one thing that it does tell you is I want grams per mil. Okay, so 3, rearrange the formula. Do I need to do anything? No, because that is. So if I want to find density, density is mass divided by volume. So I divide mass by volume. But now density, they want it in grams per mil. Do I have to do anything with units? What? So my 678 milligrams, I need to make sure that it's in grams. So 678 milligrams, I need to convert it to grams. Again, since grams is one of the units, I can do it in a single step. 678 milligrams times the line. Remember, the unit you start with always goes on the bottom in the first step. This one, the unit I want, goes on top. Milli always gets the 1,000, so I have to take 678 and divide it by 1,000. So I've got 0.678 grams. So now my units are right because I want grams divided by mil. Volume is already in milliliters, so I'm good with that. So 0.678 grams divided by 0.17 milliliters. Comes out as 3.988235294. And that's grams per mil. Can I keep all that? Okay, so now I got to go back up to the very top. And that's what I always do, is just go back to the problem. How many significant figures in 678? 3. How many significant figures? Whoop, come back. In 0.17? Just 2. So coming down here, the first 2 significant figures from the left is the 3.9. The next number's an 8. So what's that going to do?
Make that a 4.
So it'll be a 4. So is that right?
Add a decimal.
Add a decimal and a 0. That's 2 significant figures. So I'd have 4.0 grams per mil. Okay, so there's sort of the steps. At the end of class, I'm going to give you your note card that you can kind of like start working on. So if things like that, like writing those things out, one, practice them. There are density calculation problems in your e-text. There's also ones in your homework. So practice those ones. Practice going through them in those steps. Math is very much just like muscles. Like you just got to practice them and they get more and more familiar the more that you practice them. So the rest of this chapter is really talking about just other units that we're going to talk about. And the one I really want to just cover, just to make sure everybody is familiar with it, is temperature. It's pretty much the only other measurement thing we're going to talk about. So remember that temperature is a measurement of the hotness or coldness of something. I always think of temperature as being how much these molecules are vibrating, because that's their active energy. The higher their temperature, the higher they're vibrating. So solids, liquids, or gases, which ones have the highest vibrational activity? Solids, liquids, or gases, which ones do you think are vibrating the most? Solids have to actually slow down to fit tightly together. They have the lowest vibration, because the more you vibrate, the more room you need. Okay, so gases are the ones that actually have the highest vibrational activity. Gases, if you look at solids versus liquids versus gases of any substance, the gases will always have the highest temperature. Solids will always have the lowest temperature if you're talking about the same thing, like water, right? So if we have ice, then that we know is going to be like 30 degrees Fahrenheit. Is it ice? But when it's 50 degrees Fahrenheit, now it's going to be liquid water. And if it's up at 250 degrees Fahrenheit, now it's going to be a gas. So as we increase the temperature, those molecules vibrate and they require more space to be able to do that. So Fahrenheit. Do you know that the United States is like pretty much it? Nobody else in the world uses Fahrenheit but us. Yeah, everywhere else they use Celsius. So I will tell you, Fahrenheit was originally developed in Europe, and it was based on environmental temperatures. So they measured the coldest day that happened over multiple years, and they said, we're going to make that 0. So you know that that's pretty cold, okay? Because 32 degrees is the freezing point of water. So minus 32, like this must have happened like in Finland or Norway, like up in the northern mountain areas. So this was all environmental. So 0 degrees Fahrenheit was the coldest day recorded. 100 degrees Fahrenheit, they clearly didn't live in North Carolina because it would have ended up being higher than that. But the 100 degrees Fahrenheit number was the hottest day. So that's their range, was basically the environmental. Really cold day, really hot day. We'll make that 0 and 100. Celsius, on the other hand, kind of like density. Celsius is based on water. So 0 degrees Celsius is the freezing point of water. 100 degrees Celsius is the boiling point of water. So they use the characteristics, the freezing and boiling points of water as being the Celsius scale. Rather than the environmental differences. So 0 degrees Celsius all the way to 100 degrees Celsius is based on characteristics of water. So one thing I'll tell you is they don't have the same scale. Okay? So freezing point and boiling points of water, that is the 0 and 100 degree scale for Celsius. Whereas Fahrenheit, it's environmental temperatures. So in this, there's really kind of like 4 that you should know. So 1, the freezing point of water or melting point. So the freezing point of water, I told you in Celsius, is 0 degrees Celsius. What is that in Fahrenheit? 32. So you should know that those are equal. That 0 degrees Celsius and 32 degrees Fahrenheit is the same. Same thing with the boiling point of water. You should know these. The boiling point of water, we said in Celsius is 100. That's when water boils, is 100 degrees Celsius. What is that in Fahrenheit? 212. Now the other ones. One is what I consider room temperature. Okay, so room temperature, and here it's a little cooler than it was last week, which is not a bad thing. But somewhere around between 70 and 75 is what most people think of as kind of a room temperature. Most people like to have the house close to 75. It's hot. 70? Better? We're not under. Anybody in the 60s?
Yes.
I love that temperature, but I am not going to put my air conditioner down that low because it can't keep up with how hot it is. But that 75 degrees Fahrenheit, 70 to 75, that is 25 degrees Celsius. So when they say it's 25, that's kind of like normal, warm, but not super hot. That's why when they start talking about 30-degree days, that's when they're talking about days when it's getting close to 90. And you would think that people were going to, it's really funny in Europe, and they're like, it's all 30 degrees. Like, everybody's going to fall over, and I'm like, it's like that every day here. Okay? And then if it goes below 20, then you're starting to get down into the lower 60s, down into the 50s. When you're talking about 20 degrees Celsius, 10 degrees Celsius, that's down in the 40s, mid 40s. So, because you got to go all the way down to 0 degrees Celsius to get down to 32. But so those are kind of like the spans. The other one to know is body temperature. So body temperature for somebody that doesn't have a fever is what? 98.6. So 98.6 degrees Fahrenheit is considered normal body temperature. Does that mean everybody has a body temperature of 98.6? No. Well, it's kind of like there's really considered like a range. Anywhere from about 97 all the way up to 99, that's kind of the range. But on average, 98.6 is about the norm. That corresponds to what in Celsius? 37. So 37 degrees, that's considered normal. Now, when we go above 99, then they start talking about
A fever.
hyperthermia. We're going to use the term hyper quite a bit. So hyper means what? Too high. I always think of the hyperactive kid. They're too active, okay? They're higher activity than normal. So always think hyper means above normal, elevated, higher than it should be. Thermia is heat, right? So hyperthermia is higher heat than you should have. That's considered a fever. So they say if you're an adult, it's not the same if you're a kid, but if you're an adult and you have a fever up to 101, they say you really shouldn't take anything for it. Why? What does it do? What is a fever? It's actually beneficial. When do you have a fever? Because there's some kind of infection. It might be viral infection, it might be bacterial infection, but if you have a fever, you're having some kind of immune response. In fact, a low-grade fever promotes immune function. It actually makes your white blood cells more active. So if you can tolerate it, having a low-grade fever actually helps your immune system work better. Not so for little kids, because little kids can go from having a fever of 100 to what? They can have 104 fever like in a half an hour, and it's because they're so small. So little kids, you really watch them, especially infants and toddlers, they have such a small body volume that their body temperatures can change rapidly. So if you're like, oh, it's only 99, you really have to watch it about every half an hour because it could go from 99 up into the 101, 102s really fast because they're so little. But for an adult, for a healthy adult, so we're talking about 150 pounds and up, having a fever up to 101 is actually not a bad thing if you can tolerate it. Some people can't. Some people are just like, I can't take it. Like they feel terrible, makes them feel worse. But that's what a fever is. The problem comes into play is you don't want it to go much over because if it goes above 104, you can have a condition where you may actually have convulsions. You could go into a coma. And temperatures above 104 can actually cause neurons, brain cells, to die. And if they die, they don't grow back. So that can cause irreversible brain damage. But a fever in and of itself, low-grade fevers are not always a terrible thing to have, just makes you feel terrible. But it actually does stimulate your immune system. Okay. The other one, though, that's interesting is hypothermia. So hyper, always think elevated. Hyper goes too high. Hypo means it's low. Like hypo has an O, like low. So that's how I always thought of it. So hypothermia means your temperature is too low. If your temperature drops below 95, in these conditions, though, your body reacts a little bit differently. Instead of things falling apart, things just slow down. So you find slowed breathing, slowed respiratory rate, slowed heart rate. Everything, all your vitals will begin to slow down. And they don't die as quickly. Things don't stop working completely. They just get slower and slower and slower. So when could this happen? Out in the cold too long. So I always think of people that fall in icy water. Okay. So they fall like the Titanic. You remember, did you see the movie Titanic? We'll be fine. We're just going to sit here. Right? And so they just get slower and slower and slower. But in fact, your body temperature can drop down into the 60s, 70s from the normal 90, 98.6. Everything can stop. And they check your heart rate, check your blood pressure, nothing. And they're like, she's dead. Well, she's just really, really cold. And they have found that they have been able to warm people up if they do it slowly and carefully. When they get to about 95 degrees, the heart will automatically start beating again. And so blood that stopped moving will actually begin to flow again. They have to be careful how fast they do it. They have to be careful which organs get warmed up as fast. But keeping things cold slows cell activity. So what is the temperature inside of a surgery room? Very cold. They bring you in, you're like, oh my gosh. They keep it really cold because that actually slows cell activity. So that means things aren't going to fall apart quite as fast. So it's actually a benefit having it colder. So you can oftentimes cool somebody down as a way of slowing activity. Warming them back up does not always have a negative effect. So hyper and hypo, just two terms to bring in because we're going to talk about hyperthyroidism, hypothyroidism. We're going to talk about hyperglycemia, hypoglycemia. So we're going to be talking about that over the semester. So why I wanted to bring one of those in. Okay, so this pretty much finishes chapter 1. So in chapter 2, I want to go into the beginning part of chapter 2, and we'll finish this up on Wednesday. Chapter 2, if you didn't grab a periodic table and you don't have your paper periodic table, you definitely are going to need a periodic table for this part because this introduces the particles that make up atoms. So you saw this in the pre-lecture stuff, okay? So in this, subatomic particles, these are the 3 basic particles that make up an atom. Now, there are smaller subatomic particles, but we're not going to talk about them. There's like these weird quarks and neutrinos and stuff. We're not going to talk about them. These are the ones that really are involved in chemical bonds, involved in how atoms behave. So these are the ones we're going to talk about. So we have the 3. So there's protons, neutrons, and electrons. If we were going to draw an atom, so here's the atom. A-T-O-M, atom. We're going to, it would be, did you print any other PowerPoints off? So you got your all the PowerPoints are posted in Moodle, and so you can like go and print all of those PowerPoints. If you liked them written like as the notes, like I gave you as the handout on the first night. If you like those, you can print those at the library. They will still it was free all last week. They will still let you print up to 10 pages free every day. So like you could go before class, print off 10 without having to pay for anything. So that's always an option. So in this one, if you don't have yours, then you're just going to have to take notes on these, and then you can download and look at these ones later as well. Protons, neutrons, and electrons. They differ in a couple of ways. So one, they differ in terms of their location. So if we look at the atom, there's this little tiny spot in the very center. That little tiny spot they called the nucleus. And the nucleus is where they find protons and neutrons. Protons and neutrons together are in the nucleus, so that is one way that they are similar. Protons and neutrons are also similar because they have mass. But they're not identical because protons have a positive charge, neutrons don't have a charge. So you'll oftentimes see a proton written a P with a little plus. You'll see a neutron written as an N with a little 0, which means like no charge, like neutral. So they call it a little not sign. Those are in the nucleus. And in fact, the nucleus takes up 0.005% of the volume of the atom. So it's in this really small, very center, like 1/2000th the size of the atom. All the rest of the atom is mostly empty space. So they just call it the area outside the nucleus. And moving around in this area are these very small, negatively charged particles that are called electrons. So you will oftentimes see electrons written as an E. They're negatively charged, so they'll have a E with a little negative sign. So P will end up being the plus, N's is not, but the E ends up with the negative. Compared to protons and neutrons, electrons are very small. So their mass, if you look, it's 0.0005 compared to protons and neutrons, which would have a mass of 1. So they're very small. So they say that their mass is like negligible. Electrons have mass because remember, they can't be matter if they don't have mass. You have to have mass and take up space. Electrons do have mass, but it's so small, it doesn't affect the mass of the atom as a whole. The mass of the atom is really based on the number of protons and the number of neutrons that that atom has. So I always think of electrons like little particles of energy that are in constant motion. So they don't just sit here, they're constantly moving. So they're like always moving, and they actually move in certain like orientations or orbitals. But most of the space outside of that nucleus is just empty space with an electron flinging by every once in a while. So they tried to come up and say, okay, well, how big are atoms? Okay, so if we measured one atom, (21, 22, 23, 24), about 25. That's how many grams one atom would weigh. Super, super, super small. In fact, our strongest electron microscopes can only make out like the shadow of really big solid atoms. Like if you looked at like gold atoms side by side, we can magnify them and you can actually see like the outline of these just blobs. That's about as good as we can. That's how small they are. Our microscopes aren't even strong enough to be able to see them individually yet. So that's one atom. So they said, we can't use all those zeros. So let's talk about a general size. So they said, okay, well, we know that hydrogen is really small. Hydrogen seems to be the smallest of all of the elements. And so then they started comparing and they said, well, kind of like they did with water. And they said, well, we're going to make the density of water 1 gram per mil. And we'll base temperature of water 0 and 100 degrees. They said, instead of using water, we're just going to talk about carbon. Carbon became the standard. Okay. So carbon, which is C, one atom of carbon has 6 protons and 6 neutrons. They know that protons and neutrons have mass. So they said, okay, we're going to say that carbon then has a mass of 12. And we're not going to say grams because that's like one atom doesn't have that mass in terms of grams. But we're going to say carbon as an element has this mass of 12. We're going to use the term atomic mass units, or AMU. All it is, instead of being a measurable amount, it's like a relative amount. So we're just going to say carbon has a mass of 12 because it has 6 protons and 6 neutrons. Electrons don't affect the mass at all. So we'll say it has 12 AMUs. And then everything else can kind of be compared to that. They said, okay, so hydrogen. Hydrogen only has 1 proton. So if hydrogen only has 1 proton, what would its AMUs be? If every proton and every neutron is equal, it has 1 AMU, that means that hydrogen, which has just 1 proton, would have a mass of 1. So you'd say it's just 1 AMU. It's just a relative counting. Every proton will give the atom a mass of 1. Every neutron will give an atom a mass of 1. So they started to look at how on the periodic table, do you see the number above? The number above every symbol is called the atomic number. Go in here. The number above the symbol is the atomic number. The atomic number tells you the number of protons. So if you're looking at your periodic table, this is why I say, like, you don't ever have to memorize anything on the periodic table. You just have to know how to use it. So if I look at nitrogen, N, what's the number above? 7. The number below? 14.0001. Okay. So with this, the number 7 is the atomic number. That number tells me how many protons. That number also tells me how many electrons. So the 7 tells me that there are 7 protons in nitrogen. An atom with 7 protons, which are positively charged, in order for it to be a neutral atom, the number of positive and negative charges have to be the same. So if protons are positive, electrons are negative, the atomic number is also going to tell me how many electrons. So don't even have to do any math.
So how many neutrons?
So we got to figure that out. Okay? So in a neutral atom, the number of protons is the same as the number of electrons. So the atomic number, the whole number at the top, tells you numbers of protons and electrons. Well, I know protons and neutrons have mass. This number down here is the atomic mass. So the number underneath with the decimals tells me the number of protons and neutrons. I just have to round it to a whole number. So I would take 14.01 and I would round it to what? 14. And then how do I figure out the number of neutrons? Subtract. So if I take 14 and subtract the atomic number, take the atomic mass, round it to a whole number, subtract the atomic number, That'll tell me the number of neutrons, which in this one would be 7. So I don't have to memorize that. I've always got a periodic table. The whole number at the top always tells you numbers of protons and electrons. The atomic mass, rounded to a whole number, minus the atomic number will tell you numbers of neutrons. So here's like lithium, Li. So if you look at lithium, the number above tells me that I have 3 protons, right? Because it's atomic number 3. It also tells me that I have 3 little electrons running around. Now, if I look at the atomic mass, what is it? 6.94? 1 is the atomic mass. That would round to what? So I'd round that to 7, subtract 3, and that would tell me that I have 4 neutrons. That's all. So I could figure out the numbers of protons, neutrons, and electrons for all 30 of the elements that you need to know. Right? This next one, carbon. Carbon is 6. It's 12.01. So I know that I have 6 protons. You can count 6 little red balls in there. I know that I have 6 electrons. You can count 6 little tiny blue dots in there. And then if I take 12 minus 6, that will tell me that I've got 6 neutrons there. So here's a couple. So you tell me. For the first one, number 1, tell me its name. These are all ones, well, not all of them. The first one you should know. Ag is, I heard it, not gold. Gold is Au, silver. So this one is silver. Find it on the periodic table. How many protons? $47. So what else do I have 47 of? And electrons, right? Put a note to yourself. Protons and electrons will always be equal. P equals E. Okay? Protons equals electrons. P equals E. Now, how do I figure out numbers of neutrons? Okay, so 108. So it starts off, when you look at it up there, it's like 107.868. Round it to a whole number, subtract 47. So that would be what? 61. Na. What does Na stand for? Sodium. How many protons? 11. How many electrons? 11. Right? Because remember, those are the same. P equals E. Because I always put this on a test, and people always flip the P's and the N's and the E's. And I'm like, why? Like, these are ones you should not miss because they're not that bad. Remember, positive protons equals negative electrons. Okay? All right, now how do I figure out how many neutrons? So 23 from minus 11. So that would be 12. You just subtract the 2 numbers, the bigger number from the smaller number. Okay, just round the bigger number to a whole number. So TH, I haven't told you that, but that is thorium. That's not one I would ask you, but it is named after the god Thor.
It's raining outside. If you guys windows crack, my eyes are cracked. I mean, it's really raining hard.
Oh, it is?
Yeah.
I couldn't hear it. 4. So positive protons equals negative electrons. So P with the plus equals E with the minus, right? And that's always the top number. So on the periodic table, the top number is always numbers of protons, numbers, and electrons. The neutrons just subtract the 2 numbers on the periodic table. Take the decimal number, round it to a whole number, and subtract them. That's neutrons. Okay? So subtracting the numbers tells you neutrons. So if I find thorium, where is it? It's way down at the bottom. It is atomic number 90. So that tells you 90 protons and 90 electrons. How many neutrons? I have to take 238 minus 90. So 1, oh, is that the same? What did you get? 232? The number I got, I was just looking on that. I was looking on the board right there. So 232 minus 90 is 142. Hg, you should know, that is what? Mercury. Right? So remember, you got the 30. So I could ask you the name or the element, the name or the symbol of those 30 that I gave you. Mercury being 1, silver being 1, Zn being 1, sodium being 1. How many protons? 80. So that means you also have 80 electrons. And then to figure out neutrons, it's 1. It's 1. I don't know them all. I mean, I know all their names and symbols, but I don't know their atomic masses off the top of my head. Yeah, so that's 201. 201 minus 80, so that would be 121. Okay? Just take that number, round it to get your answer. What is Zn? Zinc. And that's atomic number 30. So that means 30 protons and 30 electrons. Positive protons equals negative electrons. And how many neutrons? 35. It took 65 minus 30 to get 35 as that answer. This one's not one you have to know. This is Krypton. Superman's challenge. It's on the very far right column. Kr, atomic number is 36. Right, so that tells you protons and electrons. And then I've got to take 83.8 rounds to 84. And then I'm going to subtract 36, not 84. I'm going to subtract 36. 48. Okay, so one thing to notice, little atoms like hydrogen, helium, carbon, nitrogen, they have kind of like equal numbers. Protons, neutrons, electrons, they're pretty close, right? So like carbon, if you look at carbon, carbon's got 6 protons, 6 neutrons, 6 electrons. If I look at even looking at sodium, see how I have 11 protons, 11 electrons, and 12 neutrons. So they tend to be pretty close in number with the small elements. But look at this. What changed? Protons and electrons are still the same, but neutrons are a lot more, right? 90 to 142. That's like 1.5 times, even more than that. So bigger elements, as you go across and get further and further down into the periodic table, larger elements start having more neutrons. Even krypton, which is 36, it has 36 protons and electrons, but 48 neutrons. So that's like a third more. So what they found was, especially not with all elements, but with some elements, they had different numbers of neutrons that were possible. So they began to write them in a little bit different format. So I have the format now on the periodic table. So if I ask you any of those 30s, you should be able to tell me the name, the symbol, the number of protons, neutrons, and electrons based on the periodic table. But they said, what if I just took one atom of carbon instead of just looking at elements of the element carbon as a whole? So you can write it in what they call symbolic notation. How does that look different than the periodic table? And I didn't make this rule. Do you see the numbers are switched? Why? Like, I don't know why. See how it looks like this on the periodic table? Okay. Symbolic notation always puts the atomic mass on the top, the atomic number on the bottom. And it's always a whole number this way, because this is like literally talking about one atom of carbon. One atom of carbon would have a mass number of 12, an atomic number of 6. Carbon always has an atomic number of 6. That's what defines carbon. Okay, so this, notice that 6 is always the same. But if it has a mass number, then think about this. This is talking about literally like one atom. And so we could say this one atom of carbon has 6 protons, 6 neutrons, 6 electrons. Okay? You're still finding it the same way. The atomic number is on the bottom in this one, in front, like it's a subscript, but it's still the atomic number. Still tells you the number of protons, protons and electrons. The mass number is protons and neutrons, so I just have to subtract. So this one, I think it sets it up easier to subtract because 12 minus 6, you can kind of do it on top that way. Okay? But just know this is another, these are 2 different ways that you might see these written. Here's another way. You might see it written as this. They might call it carbon 12. So carbon 12 is an atom of carbon with a mass of 12. Yeah, so we're getting there. So that's this is the mass number. So these are 3 different ways that I might write an element. If I have the name of the symbol, and I would only use the symbols, the 30 that you need to know, because I want you to be able to look at the periodic table. So like you should know like copper and zinc and gold and mercury, the ones that I gave you, as well as that 1 through 20. But I might have that name. So if I wrote so there's an example. So if I put copper, say if I said copper 64. So first, you got to find copper on the periodic table. Where is it? What is its symbol? It is?
24.
No. Copper is? Nope. There's cobalt. Cu. So remember, that's one of the ones that you have to, so some of those you've got to make sure you go back and look at those names. I'm not going to use but the 30 we talked about, but you got to be able to pick that one out. So when you find Cu, how many protons? 29. So I know it's 29 protons. I know there's also 29 neutrons. And in this one, how many, or sorry, not neutrons, sorry, that should say electrons. And then how many neutrons? 35. I got to just subtract. So I just take 64 and subtract the atomic number. If I'm given it this way, then that's like saying 1 atom of carbon 64. So this is an atom of carbon with a mass of 64. So I know there's 29 protons, 29 electrons. See atomic number 29 on the periodic table? So Cu is copper. I know in that copper 64, 64 tells me the mass. And I know the mass is protons and neutrons. So I can take and subtract the mass from my atomic number, and that'll tell me the number of protons. Or sorry, the number of neutrons, Lord. So I knew this, 64 minus 29 is how I get 35. Okay? So I'm just showing you different ways that they refer to and talk about elements. They might just use it according to the periodic table. They might use that symbolic notation. They might use the name of the element with its mass afterwards. All of those are the same. Oh, and I got to stop. Okay? So we'll do a couple more of these, and then we're going to talk about where she was just going. We're going to talk about isotopes, because isotopes have different numbers of neutrons. Okay? And we're going to apply this to some health aspects about radiation and radiation chemistry. That's really like, not only does chapter 2 introduce protons, neutrons, and electrons, but it talks about uses of radiation in terms of health. Okay?
So, my question is, so the homework that this right here is due today?
So, okay, so in every, hold on, not that, this.